All right, so here's basically how experiment 1 works. We have a spring attached to this pole, and there's a hanger. The hanger weighs 50 grams, and there's a measuring stick right next to it. And so I can measure the position that the hanger, which the hanger lies, and I can add mass onto that. So I will add mass. Okay, when I add mass, you can see that as I add mass, the hanger moves down. I will add some more mass, the hanger will move down a little bit more. What you're going to do is a table that tells you the amount of mass for the hanger and the added weights on top of it, and the location here of the hanger. Now, from the amount of mass, you can find the weight, which is pulling down, and all of these measurements were made when the mass was not accelerating at all. So you know then the spring force, the force that the spring exerts pulling this thing up, is going to cancel out exactly the weight that it's pulling down on this thing, right? Because there's no acceleration in y. So the spring force pulling up and the weight pulling down are canceling each other out. And then what you can make is a plot of the spring force as a function of this position here on the meter stick. And what you should see is that as the spring force increases, the distance, the amount that this spring gets stretched out also increases. And that means that if you make a plot of that, one consequence of Hooke's law says that spring force is equal to minus k, the spring constant, times the displacement of the spring from its equilibrium position. What that means is if you take the spring force and plot it versus that position, you'll get a straight line, and the slope of that line will be k, the spring constant for this particular spring that everybody has in lab. So you can make a measurement, you can do a regression analysis, make a measurement on k, the spring constant. You're also going to get an intercept out of it. The intercept is really not that interesting just because it's hard to find the exact equilibrium position of the spring in this case because the spring itself has weight, the spring itself has some mass, so it stretches itself out a little bit. So don't worry about the intercept. It doesn't matter if it's large, if it's small, if it's zero, it doesn't really matter. But the slope will tell you the spring constant k, and the uncertainty on the slope will tell you the uncertainty on the spring constant. Okay, good luck. So in experiment 2, we're going to measure the same thing, but we're going to use oscillations. First, I just want to talk about what it is about the spring force that gives you oscillations when you don't see things oscillating due to gravity and due to normal forces and stuff like that all the time. Okay. So the reason is, basically in a nutshell, because that force here depends on, has this position dependence to it. And that means that the thing can move and the force will change, and so that can bring about this oscillatory motion. So let's just simplify what we're working with here. So the vertical hangers that you have 2 forces. Let's just isolate ourselves to one dimension with only one force. So let's say that I have a spring attached here. It's attached to a block, say of mass m. There is a floor here that is frictionless, so mu is 0. Okay? I will set, say, this position here to be the equilibrium. So this is the equilibrium position of the spring, and I will set x equals 0 at the equilibrium location. Okay? So, and I will set right that way, say, to be positive x. Now, the forces in X here, there's only one, right? So the net force in X then is just that spring force. That's the only force acting on it, because friction is, because it's frictionless. And the spring force in this case is going to be minus K times X, right? X is just the location of the block. Since I set the equilibrium position at X equals 0, the displacement from equilibrium just simplifies down to just simply X, the coordinate. Okay? Now, since that's the net force in X, that is equal to, right, mass times the acceleration in X. Okay? And we've been talking about this now quite a bit, that if you want to go from position to velocity or velocity to acceleration, you're going to use a derivative, right? Yes, you guys have seen me draw this multiple times, right? Cool. So, velocity is the derivative dt of position versus time function. And acceleration is the derivative ddt of the velocity versus time function. Or in other words, the acceleration is the derivative of, if I take and just stick this in for v there, it's the derivative of the position versus time curve. Okay? So, take the derivative of position as a function of time with respect to time. Then take that derivative again. That's called the second derivative. The second derivative of position with respect to time is the acceleration. d squared x dt squared is the way that we write this. So this is a second derivative. It just means you do that derivative thing twice. Okay? So everybody's talking about derivatives in their calculus class now? Yeah? So this is how we write that. Acceleration is d squared x dt squared, or the second derivative of position. Now, I'm just going to stick that in here. Okay. So what we have then is minus kx equals m times d squared x dt squared. Okay, this is what's called a differential equation. The differential equation is something that relates a function to the derivatives of that function. Right? So x is not a single value in here. Right? X is a family. X is a function. It's a function of time. So you don't need to know how to solve differential equations in order to take this class. It's not a prerequisite for this class. You all will take a differential equations class at some point. And when you do, you will find out that all of the stuff that I'm going to tell you right now is true. But I'm not going to be able to derive all of this for you because it's beyond the scope of this class to derive it. So this is a differential equation. It's a second order differential equation because the highest order derivative that we find in here is two derivatives. And I can even take and add, say, kx over to the other side and get m d squared x dt squared plus kx equals 0. And that means that this is a second order homogeneous differential equation. Homogeneous means that I can get this, the function and its derivatives all on one side, and it'll be equal to 0 on the other side. So if I had a little more complicated setup, say where I put a motor in here, like attach the motor to the spring that was kind of driving an oscillation in here, then I would have to put on the left-hand side here, I couldn't have 0. I would have to have some kind of function of time that describes this, this driving force that gets pushed into the system. Okay, but this one's nice and simple. It's a linear second order homogeneous differential equation. all linear second-order homogeneous differential equations have a solution of exactly the same form. Okay, and it looks something like this. The position as a function of time that satisfies this equation is going to be equal to, say, some constant a times some kind of trig function, you could pick sine or cosine, times some omega times t, plus some kind of phase angle delta. Okay? So position as a function of time is going to be some constant times some either sine or cosine, right? Notice here, if this phase angle, this is called the phase angle. It's just a matter of like where you are in the oscillation at time 0. If that phase angle was like minus pi over 2, then this whole thing would just be a sine function. Okay, so it doesn't really matter if it's sine or cosine. And I don't really care too much about the phase angle because it's all, you can always change your time coordinates so that it's 0 anyway. So there's two things that are important here. There's an A and there's an omega. So this is an omega, by the way. It's not a W. It's an omega. So notice then, if I have here position as a function of time, that this thing is going to go like this, right? Like cosines do. And that makes sense because, just your physical intuition, you know how this block would move, right? If I come up here and I take, just whack this block, it's going to go, and it's going to go back and forth and back and forth and back and forth and back and forth, right? That's how springs work. So it makes sense then that our solution as a function of time goes back and forth and back and forth. Okay? So A is called the amplitude. It tells you how large the oscillation will get at its most extreme points. It'll get at most plus A, and it'll get at least, at its lowest point to minus A. Okay? And omega here is, omega is going to be a quantity that that describes basically how fast this oscillation takes place. Okay? So let me just explain. So when the argument of the cosine function goes from 0 to 2 pi, then the oscillation goes through one full cycle, right? Yeah? Good. Okay, now, let's just say omega was 1,000. Okay, omega is a very large number. Omega is 1,000. If omega is 1,000, then t only has to be 2 pi over 1,000 seconds in order to go from here all the way to there. Right, a very small number for time when omega is really large to go through one oscillation. Now, what if it's the other way around? What if omega is 1 over 1,000? So if omega is 1 over 1,000, then t has to be 2 pi times 1,000 before you get the first oscillation. Right? So if omega is really large, a small time later, you'll get back to where you started. If omega is really small, a very long time later until you get back to where you started. Okay, so omega captures something about the rate at which this oscillation takes place. Okay, omega is called the angular frequency. And it has units, so these square brackets always mean units. It has units of radians per second. That's an angular frequency. It gives us the number of radians per unit time as the oscillation is taking place. Now, this is a general solution to all homogeneous second-order differential equations that follow some kind of form like this. If I take the general solution and I stick it into the particular equation that I have derived for our exact setup here in this hypothetical block scenario, then what I will get is a relationship for omega in terms of m and k, the particular things for this particular experiment. Okay? And I'm not going to do that because it's kind of beyond the scope of this class, but what you would get is that omega is root k over m. Okay? Now, again, this should make sense. This is a measure of kind of how fast this thing goes, how fast the oscillation goes. If k is really stiff, if you have a really stiff spring, if k is really large, okay, then what's going to happen when you hit that block? It's going to go back and forth really fast, right? That's how a stiff spring would react. Whereas if you have a really low k spring, a spring that's kind of flimsy, then it's going to take some time. It takes more time to go through that oscillation. Whereas a stiff spring, you can hit it, it's going to oscillate back and forth really quickly. Okay? Similarly with the mass, right? If there's a larger mass here, mass is a measure of inertia. Inertia is the resistance to motion, right? It's going to take more time. This oscillation is going to happen slower if there's a larger mass. Okay, so both of those things should line up with your intuition pretty well. One thing that's a little bit counterintuitive is that this omega here, right, it's root k over n, there's no dependence on a at all. Okay? So that means it doesn't matter if you take this block and stretch it out just a little bit, or if you take the block and stretch it out all the way over here. It's going to take the same amount of time for it to get from one amplitude back to where it started. Okay? The speed at which this oscillation happens is independent of the amplitude, right? Of course, the actual velocity itself will be larger, but the amount of time it takes to undergo one full oscillation is going to be completely the same. Okay? All right. So enough about angular frequency. Let's put this in terms of just normal, regular, old, everyday frequency. So frequency f, which instead, so omega was the number of radians per second. This is just the number of oscillations per second. There's going to be omega over 2 pi, or in other words, 1 over 2 pi root k over m. Okay, so this will give you the number of oscillations per unit time. And the period t is 1 over the frequency, because frequency is number of oscillations per unit time. Period is amount of time per one oscillation. So the period is 1 over the frequency. In other words, it's 2 pi root m over k. Okay, now I can take this, and this is going to be helpful for me in the experiment that we're going to do. Okay, so what we're going to do is we'll take our setups that we have here. You have a Tasco sensor right here with a position, a motion sensor right here. I'll show you guys how to hook this up to your laptops in a second. But you would set this thing up here and set this up to your computer, and it will give you a measurement of exactly where this thing is at each point in its motion. And it can do this like 50 times a second. So you can get a position versus time curve like the one I have drawn on the board. And then you can measure the period, because you'll have position as a function of time. And you can measure the period for a bunch of different masses, because you can put on, say, just the 50-gram hanger, right? You can measure that period. And then you can take and put on a whole bunch of mass. Take and put on a whole bunch of mass and measure that period, right? Does it appear to be slower? It appears to be slower to me, right? When the mass goes up, period goes down. Okay. So you can do this for 6 different masses, And then you can explore this relationship and see, use this relationship between period and mass to get another measurement of the spring constant K. But this one here is a little, this would make the regression kind of hard because there's a square root in it. So I'm just going to do some math to make this easier for you. If I take this thing and square both sides, so I'm going to take that formula for the period, I'll square both sides. T squared then is going to be equal to 4 pi squared m over k. And if I multiply both sides of this by k over 4 pi squared, I'll get that m is equal to k over 4 pi squared t squared. Okay? Well, if I plot it up this way, where I have mass then on the y-axis and t squared, not t, but t squared on the x-axis, I can do this oscillation thing at 6 different masses. I will get a line. I can fit then a line to the data. The slope of that line will be k over 4 pi squared. The uncertainty on it will also be the uncertainty on k over 4 pi squared. And hopefully the intercept will go somewhere close to the origin as well. Hopefully the intercept is something that's at least close to being consistent with 0. Okay? So that's the basic idea.